All right, hello everybody. Got a hold of this question here and thought I'd provide you a little video for it. So we got this relation, and what we have is a relation on the real numbers, but we're calling it R, so that's a little extra confusing. That's okay. On the real, not all the real numbers, only the real interval from 1 to infinity. So that's all real numbers, not including 1, not including infinity, obviously, and every number between 1 and infinity. So every number greater than 1 on the real number line. And we define it so that for every x, y, any two numbers in that set, we say x is related to y if and only if one of two things could happen. One is x equals y. Those two numbers are equal. Okay? Or, that's the or symbol there in the middle, or 5x is less than y. And this is the less than symbol that's used on the real numbers, right? So if x is a real number, 5 times x is a real number, that real number must be less than the real number y in order for x to be related to y. What we're going to go about doing here is proving that R is a partial order. We're going to find all the maximal elements, all the minimal elements, and then we're going to find all the maximum elements and all the minimum elements. And we just got to go through the definitions of what those are. So on this one, first we're going to start with what is prove it's a partial order, and you can see here on the right, I've got all the definitions for that. Now, one of the things about a course on this is that you usually have to memorize these. So you want to keep that in mind. There's a ton of memorization going on here. A relation is called a partial order or partial ordering if it's reflexive, antisymmetric, and transitive. To be reflexive means everything in the set is related to itself. To be antisymmetric, there it is that for every x, y, and a, if x, y, and yx are in R, then x is equal to y. In other words, the only way x is related to y and y is related to x is if x equals y. And lastly, transitive, up here, for every x, y, and z, if x is related to y and y is related to z, then x is related to z. Okay, so those are our three things we need to prove, and we're going to go through all the steps here. So let's get to it. So this is number 1, proof. And so I'm going to show reflexivity first. So to show reflexivity, again, the definition here is for every x in A. Okay, so first thing, let x be in A. What's my set A here? I won't write A because we didn't call it A. Let x be my set, which is the open interval, 1 to infinity. Then, x equals x, if you want to say that. And so, x is related to x. And we're done. Because that's the second part. That's this whole thing right here. Because of that, we automatically get reflexivity. Okay? There's really nothing to do for reflexivity. All right, B. B is antisymmetric. Okay, so antisymmetric is down here for all x, y, and a. Great. Okay, so we start by saying let x, y be in my set, 1 to infinity, and then I've got an if statement. If x and y, yx are in R, then something else happens. Okay, so if we're doing a proof, then we get to assume the if. So we and assume that x, y, and yx are both x, y is in R. And I'll write that a little differently since we've been writing it differently like that here. X is related to y, and y is related to x. That is, well, what does it mean that x is related to y? It means 5x is less than y, or x equals y. And y is related to x. That means 5y is less than x, or y equals x. Okay? Now, if either of them was the case because of the x equals y, well, if x equals y, then y equals x. And they're both true, and we're good. Okay? But that's not what we want to show. We want to show that that's the only possibility. We need to show the conclusion here is that x must equal y. That's the only way it could be done. Okay? So let's scroll down a bit here. And let's continue on. So I need to show that x is not equal to y. Now, in order to do that, the only situation, the other possibility, is that so if x equals y, we're done. Otherwise, if x is not equal to y, then what do we have? Well, we have that 5x is less than y, and at the same time, we have that 5y is less than x. Do you see the contradiction coming? If 5x is less than y and 5y is less than x, take that first equation, 5x is less than y, and let's multiply both sides by 5. Okay, then we get 25x is less than 5y. Oh, but wait a minute, 5y is less than x. Oh, okay, so we have 25x then, combining those, is less than x. And we know x is not 0. We know x is, in fact, greater than 1, right? And so we can divide by it on both sides. And we know it's positive, so that doesn't flip the sign. And we get 25 is less than 1. Oops! Contradiction. Contradiction. Let's write that a little bit nicer. Contradiction. And so what that tells me is that x equals y. The only possibility is that x equals y, and we're done. And that proves antisymmetric. Okay. That's B. Lastly, C. Let's show transitive. And what does it mean to be transitive? Right here. So we're going to start by assuming let x, y, and z be in the set. That's our first thing. Let x, y, and z be in the interval from 1 to infinity. And we have a transitive as an if statement. If something, then something else. So we start by assuming the if. Assume that x is related to y and y is related to z. Assume that x is related to y and y is related to z. Then, what do we know? We know from the first definition, if x is related to y, then 5x is less than y, or x equals y. And at the same time, we know that 5y is less than z, or y equals z. Okay. Let's be very formal. Let's get every case here. If x equals y, then x is related to y, and so x is related to z, and we're done. Right? Because y equals z. Okay? If y equals z, then what do we have? We have oops, did I make a mistake there? If x equals y, what am I using? Let's back up. If x equals y, right, then since, let me just write all the details here, since y is related to z, then x is related to z, and we're done. That's what we need to show. If, on the other hand, y equals z, then since x is related to y, well then x is related to z because y is z, and we're done. Okay, so either way we get x is related to z. Again, that's what we're trying to get to. X must be related to z. So now I'm in the last case. So neither x equals y nor y equals z. In other words, the other two are the case. Otherwise, 5x is less than y, and 5y is less than z. And we're going to do something similar here. I'm going to take the first inequality and multiply both sides by 5. 5x is less than y. Take that and multiply by 5 on both sides. And so I get 25x is less than 5y. Oh, and 5y is less than z. So that's less than z. And so now I have 25x is less than z. Is that what I want? Not quite. I need to show that x is related to z. And so what I need to show is that 5x is less than z. Well, if 25x is less than z, is 5x less than z? Absolutely, because 25x is greater than 5x. Now, this is where the universe comes in important here. That's only true if x is bigger than 1, right? If x was 0, then those two things are equal. If x is negative, then it's the opposite, right? 25 times negative 1 is not bigger than 5 times negative 1, right? But as long as x is bigger than 1, which it is in this case, that's the universe, 1 to infinity, what we have is that's always the case. And so, therefore, 5x is less than z, which tells me then that x is related to z, and we're done. So in any of those three cases, x is always related to z. Thus, we're done all three. We showed first it's reflexive, we showed second it is antisymmetric, and we showed lastly that is transitive. Great. So we have that R is a partial order, and maybe we write that at the end. Thus, R is a partial order. Great. All right. So now we're going to jump over to find the maximal elements. I'm going to separate tab here. So first off, we need a pose set to talk about maximal elements. An element x and p is called minimal if, for every y and p, if y is less than or equal to x, then y equals x. In other words, the only thing less than or equal to x is x itself. And it's called maximal if, for every y and p, x is less than or equal to y implies y equals x. In other words, that the only thing that x is less than or equal to is x itself. Okay, so that's minimal and maximal. And then if there's only one maximal element, then it's called maximum. And if there's only one minimal element, it's called minimum. So in fact, if we find the maximal elements and there's more than one, then there is no maximum. And in the same way, if we find all the minimal elements and there's not exactly one, then there is no minimum element. Okay, so questions 2 and 3 are really the same thing. Okay, hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So, if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example. Okay, so to find the maximal elements, let's do it. So we're going to start by saying, let's let this thing be maximal. So now here it's all written with a less than or equal to. We need to write this with the R because R is what our relation is in this situation, right? And so what we're interested in is we want y is related to x. Now what I'm interested in there is to show this thing's maximal. I need that for every y in p, if x is less than or equal to y, then y is equal to x. Okay, so let's start the proof and let's see if we run into a problem. So let's pretend it was maximal, and I'm going to prove it's maximal. Then this is what I need to prove, right? For every y in p, this thing is true. Okay, so for every y in p, great, let y be in p. What's p? In this case, it's the a from the previous definition. It is the set. It is the underlying set, 1 to infinity. And it's an if-then statement. If x is less than or equal to y, then y equals x. So we assume the if. Assume that x is related to y. Now, wait a minute. What's x? Notice I didn't quantify it yet. So x is the thing I'm claiming or I'm checking is maximal. Okay? So let's say let x be some random thing, some fixed element, but in the set 1 to infinity. So assume x is related to y. Then I need to show that x equals y. Now, what I do know from the definition is that either 5x is less than y or x equals y. So x can equal y, great. Now for this particular fixed x, is it always true that 5x is not less than y? Whatever x is, whatever x is chosen, I can find a y that's big enough so that 5x is less than y. Specifically, for instance, let y be 5x plus 1. That's certainly also in the interval from 1 to infinity. If x is in 1 to infinity, then so is that y. And then clearly, because of the way I've defined that there, then x is, well, then 5x is not less than 5x plus 1. Oops. Yes, it is. 5x is less than 5x plus 1. I need that backwards. Let's get an eraser here. I need that 5x minus 1, I think. Let's try this out. That doesn't seem right. Let me see here. Whenever x is chosen, let y to be 5x minus 1. Then what? Then 5x is certainly not less than y, and those two things are not equal. Therefore, x is not related to y. That's not what I want. What do I want? I want to show that there is x is related to y, because I've assumed x is related to y. So I need to find a value for y where x is related to y through this method, not through the x equals y method. Right? I'm trying to conclude that x does not have to be equal to y. And so yes, the plus was right there. Because then what I'm looking for, then 5x is less than y, which is 5x plus 1. 5x is certainly less than 5x plus 1, always. And x is not equal to y. Yeah, so there we go. So what have I shown here? I started doing the proof, and then I stopped there because I realized there's an easy counterexample. I just need to make sure that this is the way in which they are related. So let's write this a little bit nicer now. Let x be in 1 to infinity. Then whatever x is chosen, regardless of what x is, let y be 5x plus 1, which is also in 1 to infinity. Then, yeah, maybe I'll just rewrite this now. Then, are these two things equal? Well, maybe that's not obvious. We just have a basic equation here. If x did equal 5x plus 1, well then that's 4x equals negative 1. X is negative 1 over 4. which is not in the interval from 1 to infinity. Okay? So therefore, there's nothing that'll work there to make x equal 5x plus 1. So x is not 5x plus 1, but since x is 5x is less than 5x plus 1, we have that x is related to 5x plus 1, or in other words, x is related to y. In other words, no matter what x we started with, I found a y so that x is related to y. X is less than or equal to y. What does that mean? I found, no matter what x I started with, I found something bigger than it. Right? Read the r as less than or equal to. So I found something bigger than or equal to, or bigger than, not equal to, bigger than x. Oh, therefore x is not maximal. That's the point. What I showed is that no matter what x I picked, x can't be maximal. And if x can't be maximal, and x is everything, then there's no maximal elements. Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe, as I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example. So R has no maximal elements. Just go that a little bit there for you. Okay, now can we do the same thing on the other side? Let's check. What does it mean to be minimal? Oh, by the way, if there's no maximal elements, we can conclude one more thing. R has no maximum element, right? There's only a maximum if there's exactly one maximal element. And since there's no maximal elements at all, there's no maximum. All right, so minimal. Let's check minimal. Element P is called minimal if, for every y in P, y is less than or equal to x, implies y equals x. Okay, so what's minimal? Let's check here. So again, let's try to prove x was minimal. So in the same way we started off before, let's start off this time. Let x be from 1 to infinity. I want to prove that x is minimal. It may or may not be, but let's see what happens. Then to show it's minimal, I need to do it for every y. So now let y be an element of 1 to infinity. And assume that y is related to x. Y is less than or equal to x. Okay, so I now need to conclude then that y must equal x. All right. Well, what is that? What does y less than or equal to x mean? It means 5y is less than x, or y equals x. If y equals x, we're done. And we could write that. If y equals x, we're done. If 5y is less than x, when does that happen? Can we find something to make that happen? Can we find something? Like, x is the fixed thing here. Can we show that every y, no matter what y is, 5y is less than x? No, of course not, right? X is some fixed number that I'm claiming is minimal. Can I guarantee that 5y is always less than x? No. If x is too small, if x is too small, then 5y is not going to be less than x. Right? If x is too small. So now let's erase this a little bit. And let's talk about the number, not 1, because 1's not in my set, but how about the number 2? 2 is in the set from 1 to infinity, right? And we assumed let y be any number from 1 to infinity, and assume that 2 is, y is less than or equal to 2. Y is related to r. In other words, 5y is less than 2, or y equals 2. Well, look at that. Can it ever be that 5y is less than 2? If 5y is less than 2, then y is less than 2/5. Oh, wait, that never happens. Oh, okay. There is no y, so that 5y is less than 2. And so if y is related to 2, then guess what? Y equals 2. Oh, that makes it minimal, doesn't it? That makes 2 minimal. Let me say that again. Since 2 is in the interval from 1 to infinity, let y be anything from 1 to infinity and assume that y is related to 2. Y is less than or equal to 2. Well, using our definition, that means either 5y is less than 2 or y equals 2. Which one is it? Well, it can't be 5y is less than 2 because that would mean y is less than 2/5. And we know y is bigger than 1. Y is somewhere in the interval from 1 to infinity. So it can't be the first one, so the only possibility is that y equals 2. In other words, y equals 2. 2 is minimal. Wow, and what was the key there? The key there is that this number, whatever that 2 happens to be, there's nothing special about the 2, except that when you divide this out, this number is less than 1. That's the point. If that number is less than 1, all those contradictions that just happen, happen. Right? Because y has to be greater than 1. It could be less than or equal to 1, I guess. But we got strictly less than here. Okay? So what does that mean? If that number on the right there is as big as... Oh, you're not going to erase on me? Okay. Click, erase. If that number on the right there is as big as 5, then 5y is less than 5 will be the same as y is less than 1. It won't work. And so we'll get to... Now, it doesn't have to be 5 because these are real numbers, right? This can be, say, pi. Pi is in the interval from 1 to infinity. And if 5y is less than pi, that means y is less than pi over 5, which is less than 1. And that can't happen, so y must equal pi. So in other words, it's not just 2 or 3 or 5. It's every number in this interval that's less than or equal to 5. And so what I'm going to do, I'll use a different letter for that. I'm going to call that... Let me erase all this again. Yeah, I'll just erase everything. I'll rewrite it. Okay. So I'm going to call m be in this interval from 1 to infinity with m, what do I want to say? M is less than or equal to 5. What I'm going to show then is m is actually minimal, no matter which m I picked. And the proof of that, we need to show for every y and p. Okay, so let y be in the set 1 to infinity, and assume that y is less than or equal to x. What does that mean? Y is related to m. Well then, if we've assumed that, either 5y is less than m, or y equals m. But if 5y is less than m, but m is less than or equal to 5, and so I divide, and so maybe I'll just write that a little bit nicer. If 5y is less than m, then 5y is certainly less than 5, which implies y is less than 1. Contradiction. That does not happen. Y is not less than 1 because y is in the interval from 1 to infinity. Thus, that doesn't happen. The only other possibility is that y equals m. And that's exactly the definition of m being minimal. M is minimal. So how many minimal numbers are there? Infinitely many. Every real number that's bigger than 1 and less than or equal to 5. Integers, it's only 2, 3, 4, and 5. But of course, 2.5, 2.193, pi minus 1, pi, divided by 2. Like, all these numbers in there. Every number between 1 and 5, not including 1 and including 5, every one of those numbers is minimal. Infinitely many minimal numbers, and therefore there is no minimum, because there is not exactly one minimal number. Now, we haven't quite finished the question. It said find all minimal elements. Yeah. We found that there is no minimum element, but we haven't found all the minimal elements necessarily. I now need to show that everything bigger than 5 is not minimal. Okay. So let x be in 1 to infinity, and x is bigger than 5. Then can I show that that thing is not minimal? Well, to show that thing is not minimal, I just need to find something that is less than or equal to it, right? And if what does that be? Well, I just need to find the number divided by 5. Then x divided by 5 is greater than 5 divided by 5, which is 1. And so x divided by 5 is in the interval. X divided by 5 is in the interval from 1 to infinity. But, is that what I want? Yeah. X divided by 5 times 5 is certainly less than x? No, it's not. That's equal to x. What do I want to do here? X is bigger than 5, so x over 5 is bigger than 5 over 5, which is 1. So that number, x over 5, what I want to know is, because I'm trying to find something that is less than or equal to x, right? Does x over 5 work? Is it true that x over 5 is related to 5? Well, certainly x over 5 is not equal to x. But is x over 5 related the first way? No, it's not, because 5 times x over 5 is x, which is not less than x. Okay, so those are not related. So that doesn't quite work. So what do I want here? I need a number. I need that x is bigger than 5, and therefore it doesn't work. I need a number that is slightly below that. X over 5, but still greater than 1. How do we go about that? Well, let's write this a little bit formally here. So let's back it up a bit here. No, it's not going to let me back it up. Wow, let's erase. Okay. x is bigger than 5, I'm going to use a character in epsilon here, be greater than 0, such that x is equal to 5 plus epsilon. Okay? Oops. The epsilon is the little bit bigger that x is than 5. That's what I'm interested in. Then, if I take x divided by 5, it's certainly small enough. X divided by 5 is 5 plus epsilon divided by 5, which is 1 plus epsilon over 5. And that number is certainly in the interval from 1 to infinity. All right. Again, just to clarify what we're doing here, what we've shown already is that every number from 1 to 5, every number not including 1 and less than or equal to 5, is minimal. The question now is that all the minimal numbers? Right? Is 5.1, what about 5.1? Is 5.1 minimal? And you can even check that over here. We'll play around with it a little bit. Maybe it's worth doing that real quick, just to make sure we're all on the same page. Is 5.1 minimal? 5.1. What would it mean to be 5.1 is minimal? It means that something is related to 5.1. The only way that's possible is that if y is 5.1. Certainly 5.1 is related to 5.1. We know that. But is there anything that is also related to 5.1 that's not 5.1? Yeah, sure there is. If I take 5.1 and divide it by 5, what do I get? Well, that's another way to put that is 5 and 1/10. 1/10 divided by 5, that's 1, and 1/10 divided by 5, 1/50th. Right, that's what that number is, which is 5.1 divided by 5, that's 1.150th, that's 200ths, so 0.2, right? Very small number, but bigger than 1. And so if I take, is 1.2 related to 5.1? No, because 5 times 1.2 is, 1.02. 5 times 1.02 is 5.1, which is not less than 5.1. Oh, so 1.02 doesn't work, but 1.01 will. 5 times 1.01 is 5.05, and that is less than 5.1. Ah, so there we go. That 1.01 is related to 5.1, and it's not equal to 5.1. Therefore, 5.1 is not minimal. You see what I had to do there? I had to find there's the biggest number that's not related to it. Nope, I said that wrong. The smallest number that's not related to it. If I get anything smaller than that, 5 times it will be small enough and make it now all of a sudden related. Okay, so let's see if we can finish this off. I said x is take x to be 5 plus this epsilon plus this little bit. Then I said x over 5 is equal to 1 plus epsilon over 5, which is in 1 to infinity. Then what I need is a number smaller than that. Smaller than 1 plus epsilon over 5, but still bigger than 1. Now epsilon might be a very small number, but whatever it is, I can divide it by something larger, divide by 10 say, and this number will be smaller but still bigger than 1. Then what I'm interested in is I will take 1 plus, for instance, epsilon over 10. I could do epsilon over 6, I could do epsilon over 100, or epsilon over 1,000. Doesn't matter. I just need that number, the little bit is bigger than 1. I need it to be even smaller than it is. All right, so then this is related to x, since 5 times 1 plus epsilon over 10, well, that's certainly less than 5 times 1 plus epsilon over 5, which is 5 plus epsilon, which is x. And so 5 times the thing I'm interested in is less than x. And if it needs to be said, and 1 plus epsilon over 10 is not x. Okay, you can check that. I'll leave you to write out the work there yourself if you want. Okay, 1 plus epsilon over 10 is not 5 plus epsilon. There is no positive epsilon value that makes that true. And that's it. We've now found, no matter what x value I picked greater than 5, I've shown here's a number, 1 plus epsilon over 10. That number is still bigger than 1, bigger than 1, so it's in this interval from 1 to infinity, and it's related to x. Why is it related to x? Because of this. Thus, x is not minimal. Thus, the minimal elements are, now I can explicitly say what all of them are. What are the minimal elements? They're the set of x in the interval from 1 to infinity, where x is less than or equal to 5. All real numbers that are less than or equal to 5 are minimal numbers here. And none of them are minimum, because they are all minimal. There are infinitely many minimal numbers. There's not only one, therefore there's no minimum, and those are all the minimal elements. Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So, if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.